In this example, we have two matrices and we want to multiply them together, both in different orders. Now, before we start, I want to talk a little bit about what you see here. This I matrix. Now, we call this I matrix the identity matrix, and in general, when you have an identity element in mathematics, it's a special type of element that belongs to some set, and when you apply it within a binary operation, it leaves the other elements unchanged when they are combined together. This will be a bit more clearer when we do this example, but this identity matrix here, when multiplied by this matrix A, should give us this matrix itself. That's what that definition was talking about. Now, the way that identity matrices are created, I guess, you could see that this identity matrix is a 2 by 2 identity matrix, and it's 1, 0, 0, 1. Now, if we have a 3 by 3 identity matrix, let me do it maybe down the bottom here. Our identity matrix for a 3 by 3 would look like this. And pretty much what we're looking at is a leading diagonal of 1s going in a diagonal pattern and with zeros surrounding. If it was a 4 by 4, it would be the same thing. 4 1s, 4 leading 1s, and zeros surrounding, and this is what makes up a identity matrix. And the great thing about identity matrices is that when you multiply them together with another matrix, you will produce that other matrix as long as your situation is conformable. Now, identity matrices are always square matrices, and what I mean by a square matrix is that it looks like a square. So it is a 2 by 2 for this one here. This one here is a 3 by 3. So pretty much for a matrix that is square, we're able to make it into an identity matrix. A couple of other things about identity matrices I'll probably mention a little bit after the video, but let's a little bit at the end of the video, sorry. But firstly, let's have a look at the multiplication of these two, A and I. So if we take the first one, A times I, let's just make sure they're conformable, and automatically we can see here that a 2 by 2 matrix is being multiplied by a 2 by 2 matrix. So obviously, yes, they are, and we're going to have a 2 by 2 matrix. And the opposite, I times A, is going to give us the same result as well. So we're taking this matrix and multiplying it by our identity matrix. Okay, when we do that multiplication, we're multiplying this row by this column, so it's 2 times 1, which is 2, and negative 3 times 0, which is 0, and 2 plus 0 is 2, obviously. So 2 is our first one. Let's just continue on. 2 times 0, that's 0. Negative 3 times 1, that's going to give us negative 3. Okay, next is negative 5 times 1, that's negative 5. And 4 times 0, that's 0. And the last element is negative 5 times 0, that's 0. 4 times 1 is 4. So we can see here, after multiplication, we actually produce A. So this identity matrix produces A. Let's check if that's also the same for AI. Identity matrix first, and then our A matrix to follow. And 1 times 2 is 2. 0 and negative 5 is 0, so there's a 2 there. What do we got? Negative 1 at 1 and negative 3. That is 3, negative 3. And 0 and 4 is 0. Okay, 0 and 2 is 0, 1 and negative 5, and then 0 and negative 3 is 0, 1 and 4 is 4. So we can see we produce A in both cases. Now, a couple of things to mention here. you would notice in this situation here, matrix multiplication is commutative. Only when we are applying the identity matrix is it commutative. And we can see that there. And now a couple of other things as well. You might think, do we always have to, if we're multiplying by the identity matrix, must we always multiply it by another, by a square matrix as well? Let's test for a couple of examples. Let's say we have the identity matrix, and that is a 2 by 2, right? And let's say we go ahead and multiply that by a 2 by 4 matrix. Well, according to our little trick here, these two are the same, so therefore we're going to get a resultant matrix here of a 2 by 4. And the original matrix, the non-identity matrix, was actually in the first place a 2 by 4. So we can see exactly how we can get that same matrix back. And you can do the same, but if we were to reverse this, and you may ask, is this situation commutative? Well, let's swap the matrices around. If we did the 2 by 4 first, and then multiplied it by this 2 by 2 identity matrix, you can see here that these aren't the same. So actually, we can't do this situation here because if, we just plainly can't, and it won't give us a solution at all because these two matrices are not conformable. So there's a couple of things there about identity matrices, and they're pretty interesting when you look at the whole big picture of matrices and just the place that an identity element has within a set of numbers.